In this segment, we're going to look at expression trees, which are a graphical way to represent and think about relational algebra expressions. Now we're going to use two queries on the course's 3 database to illustrate expression trees, so let's start by translating these into relational algebra form. As shown in the transcript here, those are first select name, student ID, units completed from a join of student and department, and with the units completed greater than 20. And then this one also, right there. But translate both of those into RA, please, for our first 2 in-lecture questions. And I'll show you the translations here in the notes, actually, because we are using them as the basis for expression trees. So the translations for the first one are down here, and we're going to do a student cross or a join department, and then a select with the department ID in 1 and 3 and the units completed greater than 20, and then a projection on that. And the second query is a little farther down here. We're joining course and section and term, and then doing a select on the start date being greater than 2013-11 and the average grade greater than 1.9, and then on that selection then doing a projection. So those are our 2 sample queries. Let's talk now about expression trees. An expression tree is a graphical visualization of an expression in tree form. RA expressions can be represented by such trees, as can any algebraic expression, including standard arithmetic expressions like, negative 2 plus 3 times 7, for example. Expression trees help reason about the expression's structure and also reflect the data structures commonly used to represent expressions in code, especially if the code will try to reorganize or optimize the expressions. Now, expression trees display basic quantities, like numbers, for instance, for arithmetic, or relations, as we'll see, for RA, in the leaves of the tree. And then operations are internal nodes. Each internal node has the operands that it operates on as children, whether those are simple values like the plus, or subtrees representing some sub-expression. For instance, the expression tree for minus 2 plus 3 is shown here in the notes, and the sub-expression 2 plus 3 is in a subtree representing the intermediate computation of 5. This in turn is the only child of a unary one-operand negation operator. And the result of that negation, along with 7, are the children of the final star operation. Note, or recall if you've seen them before, several important points regarding expression trees. First, computation of the expression proceeds from the bottom of the tree to the top of the tree, starting with the leaves, combining values in progressively larger sub-expressions or subtrees, and finally arriving at the root, which represents the final operation. 2. Since the structure of the tree determines the order of operations, there's no need for parentheses in the tree. 3. Most operators have 2 operands, and thus 2 children in the expression tree. But unary one-operand operations, like the minus sign, negation sign, have only 1 child in the expression tree, which is the result in this case of the 2 plus 3. And then finally, a left-to-right associative sequence, like 1 plus 2 plus 3, or 3 plus 4 plus 5, for instance, puts the first 2 operands in their own subtree, since the leftmost plus is done first. And this subtree then becomes the left child of the second plus, which is higher in the tree, combining the result of the 3 plus 4 and the 5. So, not surprisingly, your next in-lecture question is going to be to try your hand at building an expression tree for 8 times 3 plus 4 plus 5 minus 7. So, if you got it correct, what you should come up with is something like this. The 3 and the 4 are at the lowest levels in the tree because they're the first values to be combined with an addition. And then the result of that 3 plus 4 is in turn added to 5. And this subtree represents the entire parenthesized sub-expression, 3 plus 4 plus 5, and that in turn is multiplied by 8, and then the result of that has 7 subtracted from it. Now, expression trees for RA expressions are similar in concept, but the leaves are relations, not numbers. And the operations are join or projection or selection, or projection. For instance, if we look at the RA expression for our first sample answer to question 1, then as you can see in the notes, student and department are the leaves, and they're combined first with a conditional join, a theta join. The result of this join is selected upon by the unary selection operator that was here in the expression, and then the result of that select is projected upon by the unary projection operator to narrow it down to just the 2 desired columns. So, question 4. Build the expression tree for the answer to question 2. And we won't show it right now, but it is in the notes. Try to do it independently, though. Remember that join operators associate left to right, like the plus operators in the numerical examples. Okay, so the answer as shown in the notes here first combines course and section in a join, and then the result of that join is in turn joined with term. And note the similarity between that subtree and the one for 3 plus 4 plus 5 in the numerical example. And the result of those joins then is selected upon and then projected to get a final result. So, all this invites the question, why use expression trees? Aren't RA expressions or even straight-up SQL statements sufficient? The purpose of expression trees is to enable reorganization and rewriting of RA expressions to improve efficiency and to find the optimal way to carry out SQL queries in a database. In particular, the order in which different operations are performed can strongly affect query cost and time. So we need a way to represent RA expressions that allows us to reason about reorganization of them, and that can be readily represented in data structures in a database server program. And that's expression trees. So as an example of the kind of RA expression transformation one might do for efficiency, let's consider the first revision here of the first expression tree, the first RA expression tree. So we're looking at this thing right here. This revision splits the select on the 2 condition department ID in 1.3 and Unix completed greater than 20 into 2 selects, and then pushes them down below the join. So let's look at this kind of in 2 steps. Question 5. Why did we split the selection into 2 parts when we decided to apply it directly to the relations before doing the join? Well, the answer, when you think about it, is that units completed only makes sense if applied to student, and then the department ID in 1.3 only makes sense if applied to departments. We've broken it into 2 pieces that apply to the respective tables. The original selection applied to the Cartesian product of the tables. And if we push it downward in the tree to apply to the individual tables, then we need to break it up. But that brings us to the really critical question. Does the refactored selection ultimately produce the same result? If we do these selects first and then join the outcome, do we get the same thing as if we had done the join and then done the combined selection on that? And the answer is yeah, it does the same thing. I mean, if you look at the way this works, any row from student that would have made it through the join but didn't meet the units completed greater than 20 criterion would have been dropped at this select. And the same goes for any row in department that might have survived the join but then been dropped because the department ID wasn't 1 or 3. All we're doing by pushing these two conditions down here is killing those rows before they even make it into the join, in advance, so to speak. And then question 7, a follow-up on that. Reasoning intuitively, do you think that the first or the second version of the expression tree, this one or this one, would run more quickly? Which one and why? Well, when you think about it, it's reasonable to expect the second one to run more quickly. If we're going to dump these rows from student and department, we might as well do them up front before they have a chance to be joined, possibly with many partners in the other table. Now, this transformation, where we move the selection down toward the tables, is called a selection push, because it pushes a selection operation downward in the expression tree. It's perhaps the most commonly applied transformation for efficiency in query optimization, but there are others. For instance, could we do the same thing to a projection operation, pushing it further down into the tree? And the third version of the student and department query over here attempts to do exactly that. It's taking the projection up here and trying to push it down below the join. The justification here is that we are going to be eliminating some attributes anyway. We might as well do so as soon as possible. And this can work, but in a limited way. And question 8 here asks, as the diagram in the note suggests, there is a necessary attribute, question here, missing in each of the pushed down projections. What do we need to fill in for those questions in each case? Consider what the join above is going to need to do. And the answer is what we're going to have to fill in here is major ID in the left projection and department ID in the right projection. And the reason we need those is that they will be used by the join for its join condition. So in general, you can push a projection below a join. But if the join condition requires attributes that weren't retained in the top projection, then those have to be added to the pushed down projections. And note that this also explains why we kept the original projection at the top of the tree. We need it there to clean up major ID and department ID once they are no longer needed. Now, I had units completed there since that was missing. Okay, so question 9. Does pushing down a projection like this seem reasonable? Would efficiency be improved, and what efficiency gain might be had from it if so? Well, if you think about it, we'd get a little bit of savings on the left-hand side because we're throwing away some needless attributes sooner than we otherwise would. On the right-hand side, though, if you look closely, we're not going to get any advantage at all because we're already projecting every property of department there, and we're not trimming any of them out. So projection pushing is sometimes useful, but not as dramatically so as selection pushing. So question 10. Try applying selection pushing to the second query here, joining courses and terms and sections down here. Now we've made a copy of it for you to work on. So it's the same as the original right now, and you might try just editing that, making a copy yourself or doing something on pen and paper, but modifying this, and we'll do that in the slide as well. So the answer here is we're going to break that selection into two pieces, and we're going to apply one piece to course and the other piece to term below the joins. So there's a piece broken off and applied to term, and then we'll take the thing as well and bring it down and apply it to course. Like that. And we're getting a little crowded at the bottom here, so I'll move that whole thing up to make it more readable. Like that. Now, again, the point of this is to cull courses and terms early on before we bother joining them, and that should help reduce the size of the joins. Okay, so as a final point, let's look at one more expression tree transformation. As mentioned earlier, a 3-term join of courses in section and term associates left to right. So course joins with section, and then that joins with term. But we'd arrive at the same ultimate set of joins if the association were course joined with the combination of section and term, if it associated to the right instead. So question 11 is, how does the tree look if we make this change? Well, the answer is we'd have to move course up and section and term down in the join pattern, looking something like this. So is it worth doing the joins in right to left order? Wouldn't it be the same amount of work either way? To answer this, consider a simple case where the three tables after selection have 15, 10, and 5 rows respectively. If we operate in left to right order, we'd first join course and section for a total of 150 joins. And then we'd do those 150 joined rows with the 5 of term for a total of 750 further joins, and that's a grand total of 900 join operations. So answer the obvious question. The same calculation, please, for the right to left case. How many total joins do you get? If you think it through, you're going to have 10 times 5 is 50 joins to begin with, and those 50 joined with the 15 here for another 750, grand total of 800. So some advantage can be gained by rearranging the associativity of joins. Selection pushing, projection pushing, and join reassociation are just a few examples of the sort of expression tree manipulation that a query optimizer might do. A deeper coverage of query optimization is beyond the scope of this course, but it's an area well worth studying, especially if you find this brief intro interesting. Understanding how query optimizers work can help you write SQL that runs more quickly, and it's an important part of implementing database management systems.